Good afternoon, everyone. My name is Temitope Omokinde. I'm a graduate student at the University of Maine in the Department of Civil Engineering, and my advisor is Professor Aaron Gannant. Today, I will be talking about the optimum condition for soil carbonation and efficient CO2 consumption in a lime-treated seed. So the motivation of this research is not far-fetched. As you can see in Figure 1, Figure 1 shows a failed pavement, and Figure 2 shows freezing and thawing pavement. So the reason the pavement failed is actually due to the fact that water finds its way down to the pavement layers, which happens to be the subgrade, which is the foundation of the pavement. So when water finds its way down to the pavement, it absorbs the water, and during freezing period, the water freezes, as you can see in Figure 2. As it freezes, as we all know that when water freezes, there's going to be the expansion in volume. So it's takes some spaces within the soil subgrade material. So when the water expands and during freezing period, during thawing, it freezes, it's going to create a vacuum. So the vacuum created within the soil pavement, within the pavement material of the subgrade, is going to lead to the failure of the structure when such pavement is subjected to some vertical load. As you all know that the load subjected to pavement material on daily basis is of high magnitude. So due to this problem, due to the unfreezing of the water, the vacuum created is going to create a void space, which is going to lead to the failure of the pavement. So, and this has caused a lot of implication on budgets for repairs and also for reconstruction, and also sometimes it can be catastrophic, causing accidents on our roadways. So to solve this problem, the subgrade material needs to be reinforced, needs to be stabilized. There should be a soil improvement techniques which will help to prevent the downward movement of water into the subgrade material, which is going to reduce the permeability of the subgrade material. So solving this problem, many solutions has been profiled, such as the use of geotextile and also the use of a cement-based soil stabilization. Actually, these approaches has been effective in the years, but they all have their limitation, they are very expensive. The use of geotextile is very expensive in the stabilization of soil, and also the use of cement-based soil carbonation is very effective, but it has some implication on the environment, because during the production of cement, there is a release of huge amount of CO2 gas into the atmosphere, which is not friendly for the environment. So to solve this problem, we need to use a material which is going to reduce the carbon footprint of the environment, which is going to reduce the carbon footprint. So using land-based soil carbonation is going to give us the opportunity to reduce the CO2 gas that was emitted during its production. Actually, the production of cement emits two gases. One, we have the process-related CO2 gas, and also we have the combustion related CO2. So the process related is actually the CO2 gas emitted during the calcination of limestone, during the production of lime, and also why the CO2 emitted from machineries, from equipment, are the combustion related emissions. So the objective of this research is to understand how some properties of the soil, such as lime content, degree of saturation, void ratio, and affect the degree of carbonation. So how these properties of the soil affect the carbonation process, that is how the void ratio, degree of saturation, affect the conversion of lime particles into calcium carbonate will be examined in the research, and also to check how some condition affects the efficiency of CO2 consumption. So from figure 3, you can see that is the test procedure. Then test setup, we have the CO2 cylinder, which is going to be as a gas tank, where the CO2 is going to be introduced into the mold. As you can see, we have the flow meter, which captures the flow rate of the CO2 into the mold, and the second flow meter captures the CO2 flow rate and properties that goes out of the gas and goes out of the mold. So as you can see, we have soil carbonation and reaction mechanism. From the figure in figure 6, soil carbonation mechanism, the CO2 gas goes into the soil matrix. it reacts with the water to form carbonic acid. The carbonic acid reacts with the lime particles to form calcium carbonate. So the black dots in the right part in the figure 6 indicates the calcium carbonate that was formed. So as you can see in figure 5, the lime cycle of lime, the life cycle of lime, which was actually to show that CO2 was recaptured during the formation of calcium carbonate. So the first stage is the calcinated process, that is, lime is produced during the calcination of limestone to form calcium oxide, and also after that calcium oxide is produced, and after that hydrated oxide, which is the one I used in the lab, was produced. So to form calcium carbonate in the presence of water and also CO2 gas, CO2 is recaptured, it forms calcium carbonate. So the lime cycle shows that calcium carbonate formation takes place, and during this formation of calcium carbonate, CO2 gas is sequestrated. So lime soil carbonation forms a carbon sink, which is very, very good, which is something we like. So from the results, we can see that as the lime content in the mix in result 5.1, as the lime content in the mix increases, the amount of calcite produced is increases. So the implication of this is that as the lime content increases, there's going to be a lot of calcium carbonate produced. So the calcium carbonate formed is going to precipitate over the lime content. So which is very difficult to convert the other lime particles that has been covered by the calcite form into calcite. So as you can see in the figure 5.1b, the sample with the least amount of lime content has the highest conversion because less calcite is produced, which gives room for more lime particles to be converted into calcium carbonate. So the implication of this is that as the lime content increases, the conversion of lime particles to calcium carbonate becomes more difficult. So figure 5.2 shows the effect of degree of saturation on the degree of carbonation. As you can see, as the lime content increases in figure 5.2a, more calcite is produced. So which means as the saturation rate increases, more calcite is produced. But because more water is available in the system for the initial dissolution of lime, and also more water is available for the dissolution of CO2 gas. So all these helps in the formation of more calcite in the host soil carbonation process. So but when we get to a saturation rate of 50%, it's very obvious. As you can see, the gas finds it difficult to move through the soil, therefore creating a gas mobility problem. So saturation rate is very good for the soil. At the same time, it's very bad when it gets to some point from the result at saturation rate of 50% upward. The gas find it difficult to move through the soil matrix, which affect the degree of carbonation. That is why we have a drop in the degree of carbonation at saturation rate of 50% and above. So the summary of this research is that as the lime content increases in the mixture, it is difficult to convert all the lime particles. So the higher the lime content, the more difficult it becomes to convert all the lime content into calcium carbonate. And also from the research, we see that as the degree of saturation increases, more calcite is produced. It enhances the degree of carbonation because more lime is going to be dissolved into the water. More water is going to be available for the dissolution of lime. So it enhances the formation of calcite. But it gets to some point that the saturation rate of 50% or above, this the CO2 finds it difficult to move through the soil matrix, creating a gas mobility problem. The expected benefit is that one, it helps in rapid strength improvement, and also the lime-based soil carbonation is a means to capture CO2, which is very, very good for the environment. It's a means to reduce the carbon footprint of lime, so which is a very good research for us. And also the future work is one, I will determine the effect of void ratio on the degree of carbonation. I will determine the effect of flow rate on the CO2 effect of flow rate on the degree of carbonation, and also I will be determining the efficiency of CO2 consumption. So I will use this. I want to use this medium to appreciate the Transportation Infrastructure Diversity Center for the funding. Thank you.